a multiple of fundamental unit numbers. Okay, and there are multiples of that. It was first discovered in a long time back in 1982 when trying to understand what is happening in the hemisphere of the BMN. This is called a Chern. Okay, just like one number, it's 2D, it's called the Chern number. Okay, so I told you about the third kind, right? Oops. I told you about the third kind, which is the semi-metals. So I'm going to tell you very quickly what and how to understand semi-metals and the type of problem that we have. Okay, so there are actually many topological insulators. Okay, not just in 1D, but you can define them in higher dimension. And they are defined by these three symmetries. This symmetries T is called the time reversal symmetry, charge conservation, which is C, and their multiplication, which is called a chiral symmetry. Okay? And you can show that these are the only 10 possibilities that can happen. 0 means that symmetry doesn't exist. 1 means that symmetry exists, and the operator squares to 1. And here, your -1 means it squares to -1. Okay? And one of the simplest models that I told you is SSH. Remember, this is 1D, and that's actually in the DD1 class. Okay? It has time reversal, it has charge conjugation, and it is the time switch. The other one I showed you is called quantum Hall effect. Okay? It actually has no symmetries. Okay? The interruptions are natural. Okay. So, quantum Hall effect actually has no symmetries. Okay? And not only does it have any symmetry, it actually is in 2 dimensions, which is this symmetry. This is chunk. Okay? And we can use these ideas to actually understand semimetals. So I'm going to talk about 3D semimetals, and there are many kinds. But if they are isolated, or they could be something like a line. Okay? And there is a new kind, which is called a nexus. So this is a projection. So I cannot draw 3D spectrum. So it's a projection of 3D in 2D. There's a single line where the spectrums are degenerated for these 3 bands, and there's one point where all 3 bands are degenerate. And hopefully I'll talk very quickly about how to understand this. Okay? This is not very interesting, but not for me. So how to understand if they're isolated? You take the point, you enclose in a sphere, the sphere is gap. The spectrum of the sphere is gap, because gap is only one point. Right? And you can use exactly the old school 2D invariant because the sphere is a 2D object. Right? And you know, if you are probably studying statistical mechanics, this is something to connect it with the Gaussian. Okay? It's like a charge enclosed in a sphere. I have no idea what it is. My laptop is dying. Anyway, so you can also do similar with the lines. You can impose a line in a sphere, which is same as 2D invariant and same as while. You can invariant, write down invariants on 2 points, 0 dimensional, if these circles are forced to be on a plane, and you can do what are called 1D invariants. Okay? But the nexus is very different. Okay? This is the picture, so this is the line where it is degenerate. This B is this horizontal curve, C is the vertical curve. Okay? And this happens because of what are called non-commuting symmetries. Okay, so these are called nexus constructs. Okay, and the problem with that is that if I want to understand that triple point in the middle, and if I enclose it in a sphere, I cannot, because these points are actually remains region.